Hello dears, this is the third part of the topic, the Cauchy problem for the non-homogeneous wave equation. In the last class, we have derived this D'Alembert's formula for the Cauchy problem of non-homogeneous wave equation. Now it remains to prove that this function is a solution of this Cauchy problem. This function is a solution of this Cauchy problem utt minus e square into uxx equal to f of x comma t, and u of x is 0 equal to f of x, ut x is 0 equal to g of x are the initial conditions. So it remains to prove that this function is a solution of this Cauchy problem. Okay, the function u in this formula is a solution of this Cauchy problem if and only if this function 1 by 2c into double integral over delta f of zeta tau d zeta d tau is a solution of the Cauchy problem. This along with the homogeneous initial conditions. Okay, that is u into is a solution of 1, the Cauchy problem 1, if and only if the function this 1 by 2c double integral over delta f of zeta tau d zeta d tau is a solution of the Cauchy problem this utt minus e square into uxx equal to f of x comma t, utt minus c square into uxx equal to f of x comma t for minus infinity less than x less than infinity t greater than 0, and u of x comma 0 equal to 0 and ut of x comma 0 equal to 0 for minus infinity less than x less than infinity. That means here we are taken only the homogeneous boundary conditions. Okay, our actual Cauchy problem is that the condition is non-homogeneous, but to prove this is a solution of this Cauchy problem, we need only to show that this function, okay, this is already proved by superposition principle. We have this also solution. So now to uh, prove this is a solution of this Cauchy problem, we need only to prove that this function is a solution of this Cauchy problem. That means with the homogeneous boundary conditions. Then only it will, that means this function satisfies the homogeneous this boundary conditions. This function if this function satisfies these boundary conditions, that means u of x is 0 equal to 0 and ut x 0 equal to 0, then only u of x 0 will be f of x and ut of x 0 will be g of x. Okay, otherwise u of x0 will be not equal to f of x plus some function will be there, or of some quantity will be there. So to make this u of x0 equal to f of x, we have to choose the condition. This is a function, this function is a solution, it satisfies u of x0 equal to 0 and ut x0 equal to 0. Okay, so now we have to show that our aim is to show that this is a solution of this Cauchy problem. Okay, we can number this as 3 and this as 4. Okay, now actually we know this is actually this function is we can name it as some v of xt, okay, for convenience. So from this v of xt is actually we have v of xt is equal to 1 by 2c into double integral over delta f of zeta tau d zeta d tau. Okay, so we already have the characteristic triangle. It was like this. Okay, Here actually, if this is here the variables are zeta and tau, so we can take this as zeta axis and this as tau axis. So take this as x comma t for an arbitrary point x comma t. So this is x and this point will be x minus some ct. This is x plus ct comma 0. Okay, the second coordinate is 0. So we know this is actually the uh, characteristics, which is zeta plus c tau equal to x plus ct. Here this point is x comma t, so this will be x, and this characteristics is nothing but zeta minus c tau equal to x minus ct, right? So uh, this is the triangle delta. This is the triangle delta. So we have the double integral over delta f of zeta tau d zeta d tau. So what will be uh, the boundaries of our variable? Okay, so we have like this. If this f of zeta tau d zeta d tau. So this is for tau and this is for zeta. So the outer integral is actually we can take the uh, outer limits actually t varies from, I mean tau varies from 0 to t. Okay, this is t. So tau varies from 0 to t and zeta varies from this line to this line. Okay, this line to this line. So zeta varies from this to this. That means here zeta is equal to x minus ct plus c tau. That is zeta from x minus c into t minus tau, right? So this is x minus ct plus c tau, x minus ct plus c tau, and to here from this to this, x zeta varies from this to this. So this is actually x plus ct minus c tau. So this can be written as x plus c into t minus tau. Okay, so we have this is v. This v can be written as this. Okay, so we can number this as 5. Now we have to show that this V satisfies these differential equation and these conditions. Okay, so this is V of xt. So clearly from this we can say that this satisfies this condition. These are the conditions we need to check. So the second condition is actually the boundary initial conditions. So u of x is 0 equals 0. So V satisfies this condition because V of x is 0 is equal to, clearly we have this uh, V of x is 0 is equal to 1 by 2c into t equals 0 here. So 0 to 0 will be there. So 0. So this satisfies this condition. Now we have to verify this condition and this differential equation. So we need to satisfy this condition and this differential equation. So we will prove this this V is a solution of this these equations 3 and 4 under the assumption that f and fx are continuous. Okay, so we are assuming f and fx are continuous. Okay, so we already proved that v of x is 0 equal to 0. Now to find the derivative, that is we need to find vt. Okay, so to find the derivative we can use the Leibniz formula. To find the derivative we can use Leibniz formula for differentiating an integral, which is nothing but dou by dou t of integral from a of t to b of t g of zeta comma t d zeta is equal to uh, integral from a of t to b of t dou g by dou g by dou t of zeta t d zeta plus g of zeta can be replaced by the upper limit g of beta b of t comma t into derivative of this b, that is beta b dash t, minus the lower limit is actually g of the lower limit, that is zeta can be replaced by b. So a of t comma t into a dash t, a dash of t. So this is the Leibniz formula. So to find the derivative we can use this formula. Okay, here our function v is this v of x comma t equal to 1 by 2c into integral tau from 0 to t integral zeta from this to this f of zeta tau d zeta t tau. Okay, so to apply this formula we can represent this inner integral as g. Okay, so this inner integral is actually with respect to zeta. So when we replace zeta by these two values, this will be a function of tau and this integral will be a function of tau and t. Okay, so we can write let g of tau comma t is equal to integral x minus c into t minus tau to x plus t into c into t minus tau g of f of zeta tau d zeta. F of zeta tau d zeta. Therefore, this can be written as in equation number 5. We have v of xt is equal to 1 by 2c into integral 0 to t, and this is g of tau comma t d tau. Okay, that is we replaced this inner integral as f of g of tau comma t. Okay, now we can apply this Leibniz rule here to find the derivative of this. So therefore vt of vt is equal to 1 by 2c into dou by dou t of integral 0 to t g of tau comma t d tau. So applying this Leibniz rule, we have this is first we can do this, that is g of b of t into t into b dash t, that is we are applying the upper limits for tau and derivatives. So we have this is equal to 1 by 2c into g of t, the upper limit is t, so g of t comma t into derivative of t, that is 1, minus g of, now we are substituting a lower in the limit, that is 0 comma t into derivative of 0, that is 0, plus integral, this integral is 0 to t dou by dou t of g of tau t d tau. Okay, that is what is this integral a of t to b of t dou by dou t of this function. Okay, so we are doing this dou by dou t of g of tau t dt d tau. Now this is equal to 1 by 2c into g of t t. Actually g is this, so when we replace tau by t we have integral x minus c into t minus t, that is this will be 0 and here also 0, so f of zeta t d zeta. Okay, so this is nothing but integral x to x when we replace tau by t. Okay, here, so f of zeta t d zeta into 1 minus this is 0 plus integral of this, that is integral 0 to t dou by dou t of g of this. So g is this, so we have to integrate x minus c into t minus tau x plus c into t minus tau f of zeta tau d zeta. This is actually g of d tau into d tau. Okay. Okay. So here we have to apply the Leibniz formula one more time. Okay, to find this in the integral of this. Okay. So this is equal to 1 by 2c into integral x to x, this is 0. So 0 plus integral 0 to t, now integral of this. By using apply by Leibniz rule, we have f of zeta can be replaced by the upper limit, that is x plus c into t minus tau comma tau into derivative of the upper limit, that is by using this replacing the upper limit into derivative of upper limit minus g of replacing this by lower limit into derivative of lower limit. Okay, so into derivative of this upper limit with respect to t, that is c. Okay, into c minus f of replacing this zeta by lower limit, that is x minus c into t minus tau comma tau into derivative of this lower limit with respect to t, that is minus c, then plus integral from x minus c into t minus tau to x plus c into t minus tau dou by dou t of this. Okay, that is dou by dou t of f of zeta tau d zeta. Okay, into d tau. Okay, now we have this is 0, dou by dou t of f of zeta tau is 0, so we have this is nothing but 1 by 2c into this integral of this only, that is here we have c, here also we have t, so c, so we can take c outside, so here it will be c by uh, c by 2c, that is we have 1 by 2 only. Okay, 1 by 2 into integral 0 to t f of x plus c into t minus tau comma tau and c taken outside minus into minus is plus f of x minus c into t minus tau comma tau. Okay, into d tau, this is 0, so into d tau. So this is actually vt of x comma t. Okay, this is vt of x comma t. So the second condition is actually vt of x comma 0. Therefore we have vt of x comma 0 is equal to 1 by 2 into integral 0 to 0, that is 0. So we have obtained that v of x0 equal to 0, v of x0 equals 0 and vt of x0 equals 0. So the initial conditions, that is v satisfies the initial conditions for this and this. Okay, so therefore v satisfies the conditions in 4. Now to show that v satisfies the PDE 3. Now we have to show that this v satisfies the PDE 3. That is, we have to show that VTT equal to, or VTT minus E square into VTT minus E square into Vxx equal to f of x comma t. We have to show that this. Okay. So for that we need to find VTT and Vxx, right? So now to find VTT, so we have to integrate once again this Vt with respect to t. Okay. So to find VTT, let we can denote this as G. Okay. Let G of tau comma t is equal to this function, that is f of x plus c into t minus tau comma tau plus f of x minus c into t minus tau comma tau. So therefore our Vt is nothing but Vt is equal to 1 by 2 into integral 0 to t g of tau comma t d tau. Okay, now we can apply the Leibniz formula. Therefore second derivative Vtt is equal to 1 by 2 into dou by dou t of integral 0 to t g of tau comma t d tau, which is nothing but 1 by 2 into g of, first we can replace tau by t, that is g of t comma t into derivative of t with respect to t, that is 1 minus g of then replace tau by 0 comma t into derivative of 0, that is 0, plus integral 0 to t dou by dou t of this g of tau comma t d tau. Okay, now this is actually, this is equal to 1 by 2 into, we have g of t comma t, g is this, so g of t comma t is nothing but we have to replace tau by t, so here that is f of x plus c into t minus tau, that is t minus t, that is 0, so this is x comma t, replacing tau by t plus f of x comma t again, that is here when we replace tau by t, this is 0 and this is t, so f of x comma t, then and this is g of t comma t minus g of 0 comma t into 0, this is 0, now plus integral of this, integral 0 to t dou by dou t of g of t comma t, so this is nothing but plus integral 0 to t dou by dou t of g of t comma t, that is this, that is f of x plus c into t minus tau comma tau plus f of x minus c into t minus tau comma tau. Okay, this is new g into d tau, right? Okay, now we have this f of x comma t plus f of x comma t divided by 2, that is f of 2 into f of x comma t divided by 2, that is f of x comma t, plus here 1 by 2 into integral of this 1 by 2 into integral 0 to t. Now what is dou by dou t of this? Dou by dou t of this is nothing but we can write like this, dou by dou t of f of, I am using this as some new function y, this f of, and this as new function z. Okay, so this is f of y comma tau plus f of z comma tau into d tau, where y equal is for convenience x plus c into t minus tau and z is equal to x minus c into t minus tau. Okay, now by chain rule we have f of x comma t plus 1 by 2 integral 0 to t. By chain rule we have here dou by dou y of f, or f of y comma tau into dou y by dou t plus dou by dou tau of f into dou tau by uh, dou t, that is 0. Okay, now plus here we have dou by dou z of f of z comma tau into dou z by dou t plus dou by dou z of dou by dou tau of f into dou tau by dou t, that is also 0. So into d tau. Okay, so this is nothing but f of x comma t plus 1 by 2 into integral 0 to t dou by dou y of this into dou y by dou t. Dou y by dou t is c. So this is nothing but dou by uh, dou y of f of y comma tau into c plus dou by dou z of f of z comma tau into dou z by dou t is also minus c. Okay, into d tau. Now this is equal to, so we can take this c outside, so we'll have this f of x comma t plus c by 2 into integral 0 to t dou by dou y of f of y comma tau minus, here is minus c, so minus dou by dou z of f of z comma tau into d tau. Okay, so this can be written as actually this is equal to f of x comma t plus c by 2 into integral 0 to it can be written as dou by, we are using this y and z are new functions to represent this x plus c comma c into t minus tau and x minus c comma c into t minus tau. Okay, that is for convenience. So here this is actually dou by dou x of f of y is actually what was y is x plus c into t minus tau comma tau minus dou by dou x of f of x minus c into t minus tau comma tau. Okay, into d tau. It is since we have dou by dou x of f of x plus c into t minus tau comma tau is nothing but dou by dou x of this is nothing but it can be represented as dou by dou x of some f of y comma tau where y is this, where y equal to x plus c into t minus tau. Okay, so this is equal to, we can apply chain rule, dou by dou y of f of y comma tau into dou y by dou x plus dou by dou tau of f into dou tau by dou x as also 0. So this is equal to dou by dou y of f of y comma tau into dou y by dou x. Dou y by dou x is 1 here. Okay, dou y by dou x is 1. So this is, we can represent dou by dou y of f of y comma tau as dou by dou x of f of x plus c into tau minus c into t minus tau. Okay, so similarly we can represent this dou by dou z of f of z comma t as this. Okay, so in a similar way we can show that dou by dou x of f of x plus c into t minus tau into tau comma tau is equal to dou by dou z of dou by dou z of f of z comma tau where z is equal to x minus c into tau t minus tau. Okay, so we have, this is actually vt, right? So Vt of x comma t is equal to this. So this can be written as actually Vt of x comma t is equal to f of x plus t plus c by 2 into integral 0 to t. This is fx of this, like so fx of x plus c into t minus tau comma tau minus fx of x minus c into t minus tau comma tau into d tau. Okay, so we have this. This is vtt, not vt. Okay, vx and vxx will be this. Similarly, we have vx of x comma t will be 1 by 2c into integral 0 to t f of x plus c into t minus tau comma tau minus f of x minus c into t minus tau comma tau into d tau, and vxx is vxx of x comma t will be equal to 1 by 2c into integral 0 to t fx of x plus c into t minus tau comma tau uh, minus fx of x minus c into t minus tau comma tau into d tau. So we have obtained vtt equal to this and vxx equal to this. So here actually f of x comma t, right? So now from this we can write uh, this is vxx. So c square into vxx is nothing but c square by 2c into this. So this is c by 2 into this. That means which is equal to this. So this can be written as c square into vxx. Therefore, we have vtt equal to f of x comma t plus c square into vxx. That is vtt minus c square into vxx equal to f of x comma t. Therefore, V also satisfies the PDE. The PDE 3, I think. Okay, so we satisfies the PDE and it's in this initial conditions. Okay, and we satisfies this PDE and these initial conditions. So that's the proof.